A matrix is a rectangular collection of elements composed of m number of rows and n number of columns. The convention is to use capital letters for variables representing matrices. When writing the general form of a matrix, we use placeholders for values in a specific matrix, which are the lowercase of our matrix variable followed by subscripts of their relative position within the matrix's brackets. Let's say we have a specific matrix, capital B, which has 3 rows and 3 columns. We call this a 3 by 3 matrix. I'm just filling in random numbers in the brackets for this example. If we wanted to refer to a specific element of the matrix, for instance, the element that appears at row 2, column 2, we could just use its index value. That is to say, lowercase b sub 2, 2 is equal to 3. Lowercase b sub 3, 2 is equal to 1, etc. Hopefully this seems familiar to how we conceptualized and plotted in 2 dimensions, and in fact matrices are often used as domain spaces. We'll be limiting our usage of matrices to collections of equations. As a side note, when a matrix has one row and multiple columns, or one column and multiple rows, it's called a vector. If a matrix has only one row and one column, it's called a scalar. It's fine to still call these matrices as long as you specify the dimensions. Let's look at matrices in terms of systems of equations. Say we have 2 equations. 3 times a plus 2 times b equals 8, and a minus 4 times b equals -2. We can stack both sides of the equation into vectors. An equal sign between matrices only makes sense if the matrices have the same dimensions, and the equality means that the corresponding elements of the matrices are equal. Note that we have combined 2 equations into one equation. Put the equations in this form for a few reasons. One is that they are often easier to manipulate, and another is that this form is easier to input into a computer for number crunching. Once a set of equations is in matrix form, we can apply matrix algebra to our manipulations. For instance, taking our previous example, we could separate the left-hand vector into 2 separate vectors. The key here is to remember that matrix addition is element by element, so they must be of the same dimensions. We can also pull out any constants. The key here is to remember that when a scalar is multiplied by a matrix, it is multiplied by every element of the matrix. The last bit of matrix algebra we need to know is a bit tricky. What happens when a matrix is multiplied by another matrix? According to Wikipedia, multiplication of 2 matrices is defined if and only if the number of columns of the left matrix is the same as the number of rows of the right matrix. I'm going to do 3 quick examples of matrix multiplication. We are given the following 3 matrices, A, B, and C. Example 1. If possible, multiply matrices A and B. I usually physically put my hand on the first element of each matrix, then slide my left hand to the right across the columns, and my right hand down the rows, tracing out which elements I'll be using. In this case, A times E plus B times F is the first element. Then I move my left hand down a row and repeat, which results in C times E plus D times F. Example 2. If possible, multiply B times A. By inspection, the number of columns of the left matrix, which is 1, is not equal to the number of rows as the right matrix, which is 2. So we cannot multiply the matrices. Example 3. If possible, multiply A times C. The number of columns in the left hand is the same as the number of rows on the right hand, so the multiplication is valid. To multiply, use the same method as we did in example 1. A times G plus B times I is the element 1, 1. A times H plus B times J is the element 1, 2, and so on. If you're using the method of placing your fingers on the matrix and sliding, the trick is to note where your fingers start. That is the index of the resulting multiplication and addition. That's pretty much all you're going to need in terms of understanding matrices up through advanced signal processing. It can get easily confusing though, so if it's been a while, or it's new, just work through some practice problems.